Keypoints have been widely used to abstract structures from images. To discover keypoints from raw pixels, earlier methods usually rely on supervised learning, which requires large-scale dataset annotated with intensive human labor. Unsupervised methods have been developed to learn 2D keypoints from videos or interactions without human annotations. Previous works show that learned keypoints serve as an effective representation for visual control. These works, however, only focus on 2D scenarios. If applied to 3D environments directly, these methods can only learn projected keypoints on 2D planes and thus lose depth information. Thus, 2D keypoints fail to serve as a good representation for control in 3D environments. In this work, we present a method that discovers 3D keypoints from visual observation without supervision. We show the learned 3D keypoints not only capture crucial movements in the scene, but also help efficient policy learning in a variety of tasks. To learn 3D keypoints, we set up multiple cameras in the scene and feed the observation into convolutional neural networks. Our neural network then discovers a set of temporally consistent 3D keypoints via interaction with the environment in an unsupervised manner. To achieve this, our method trains keypoint discovery using a multi-view autoencoding structure. We use a keypoint encoder to parameterize 3D keypoints in the world coordinates. For each camera, a convolutional neural network encodes image into probability maps. We then extract 2D UV coordinates using a fully differentiable keypoint bottleneck. The extracted 2D coordinates are combined with depth predictions to output coordinates in camera space, which can then be unprojected to world space using camera matrices. In the fully differentiable keypoint bottleneck, we take spatial expectation of 2D coordinates from the parameterized probability map for each keypoint. This way, the extracted keypoint coordinates are associated with feature locations in the input image. All cameras predict a same set of keypoints. We use a multi-view consistency loss to penalize disagreement between predictions from different views. This way, predictions from all views must satisfy 3D geometry and capture global structures that are more visible from other views. Estimations from different views are weighted into a single set of keypoint predictions. At decoding phase, the combined keypoint estimation is projected back onto each camera plane. For each keypoint on each plane, we create a 2D Gaussian centered at projected 2D coordinates with standard deviation inversely proportional to depth. This way, the coordinates regain 2D structure, which can then be stacked and decoded to images. We use multi-view autoencoding loss to penalize reconstruction error. Since decoded images are conditioned on stacked 2D Gaussians, the loss encourages those Gaussians to center at important features projected in each view. Since 2D Gaussians are generated from predicted 3D keypoints, the loss would indirectly require the encoder to correctly predict the 3D keypoints that match these features. We jointly train control policy on top of the latent 3D keypoints. By visualizing the learned keypoints, we found that our Keypoint 3D method can learn temporally and geometrically consistent keypoints. The learned keypoints are able to track objects and robot arm consistently in the 3D space. Here we show the visualization of learned keypoints in pipelet and environment, and you can observe the learned keypoints tend to track the movements of the robot limbs. In previous section, we have shown our method can extract meaningful 3D keypoints from pixels without supervision. Now we can investigate how well reinforcement learning does on top of this unsupervised representation. To do so, we jointly train a reinforcement learning algorithm on the learned keypoints. We then compare our 3D keypoint method with state-of-the-art visual reinforcement learning methods, Curl and RED, as well as Vanilla IL. We also benchmark a baseline where we use 2D keypoints representations. We note all baselines receive the same multi-view observation. In meta world, our method outperforms all baselines in a variety of manipulation tasks. Our method also scales up to high-dimensional control task, pipelet end, as well as a low-textured variant of it. Our method is also effective in deformable object manipulation. In our scarf dressing environment, our Keypoint 3D method is the most effective one. In summary, we propose a framework to learn 3D keypoints without supervision for continuous control. We leverage multi-view autoencoding with 3D keypoint bottleneck to learn meaningful 3D keypoints. We jointly train policy learning in conjunction with keypoint learning. Our method achieves significant sample efficiency improvement in a variety of 3D environments, and the 3D keypoints learned by our method are consistent across space and time. We hope our method serves as a bridge between pixel domain and 3D control tasks. For more details, please visit our website, code, and paper in the following links.